in the space of operators acting on some vector space. Well, for physicists, this would be some just objects, the fields. And then the main feature is that if you take the product, whatever it means, then it somehow decomposes via the fields from the same theory. Well, let me write the formula. Sum over integers. Here I put z minus w to the n plus 1. Here I put y of something w. And this something are other fields. Cn. So this is the general form of the OPE, saying that if you take the product, then you can somehow consider the behavior on the diagonal z equals w, and then the behavior is expressed via the fields from the same theory. So in a sense, if you take the product of the fields, then you generate infinite number of new fields. And of course, one has to somehow understand what's that. So you have to expand and so on. But this is the idea. And actually, we can write it in a more explicit way. So this is AN B. Well, you see, the formula can be understood as you take the product of two fields, and then you expand, and you write this form, and then these are the new fields. And in a sense, this is the definition of the product. Yes, I mean, A and B can be defined as coefficients popping up in such a decomposition. But of course, for us, the situation vice versa. So we started with the definition of vertex separated algebras, and this A and B, they come up from the very definition. And after all, we are getting such a formula. So this is what we're going to discuss today, and maybe next time as well.
Sorry, A and B should be applied to the vector B?
Absolutely. Okay, so let us start. Let us start with one theorem which is important for the proof, but also important for the whole vertex separated algebra theory. So this is called the Goddard's uniqueness theorem. And it says the following. So let V be a vertex separated algebra. And A be a vector in V. So assume that A of Z is a field on V, such that A of Z is local with all fields of the form YBZ, B from V. Maybe I put it in a small b to make it compatible with the small a. And A of Z applied to the vacuum equals to Y of AZ applied to the vacuum. Then A of Z is Y of AZ. So the theorem says that you actually, in order to somehow identify a field, so in order to understand that some field is a member of the fields coming from the vertex separated algebra theory, you just need to check the value at vacuum vector. Well, of course, provided you know the locality. Okay. So what do we want to prove? So see, actually, the statement is quite strong. Yeah. So I mean, the vector space is infinite dimensional V, and we only check it at one single vector. So I mean, it's a kind of strange from the first glance. So the proof, so we have to check that for any B and V, A of Z applied to B equals to Y of AZ applied to B. Okay. So this is what we want to check. So any ideas how we can check this? Serene, how? Yes, this is a good idea. So let us indeed select us write B as Y of B, say W, applied to the vacuum at W equals 0, right? So we know that if you apply a vertex operator to a vacuum and then substitute W equals 0, then get the vector. So well, using this, we rewrite A of Z Y of B W, the vacuum should be equal to, so this is what we want to prove, should be equal to Y of AZ, Y of BW 0, and it should hold at W equals 0. Okay. Okay, and so what should be the next step? Yes, we need, so the formula, what formula you mean? We don't know it so far. No, it's a complicated theorem. So I mean, yes. Yes, absolutely. So we need to, so in principle, the idea would be that we want somehow to change the order, because we know that A of Z applied to the vacuum is Y of AZ applied to the vacuum. So we better change the order and then we are done. Yeah. But of course, we can't change the order just for free. But we know the locality. Yes, so let us use the locality saying that so there exists an n such that Z minus W to the n, and then I put here Y of BW and A of Z applied to the vacuum equals to W to the n Y of BW. So actually for any n, A of Z applied to the vacuum. Sorry. Because we know that A of Z applied to the, oops, what did I write? Y of AZ, yes. So we know that Y of, so far, yeah, not yet. I just used that this guy applied to the vacuum equals to this guy applied to the vacuum. Okay, so nothing happened so far. But now I do want to change the order, and then I'm saying that there exists an n for some n large enough. I can change the order, so meaning that z minus w to the n, a of z by bw applied to the vacuum should be equal to y of az, y of bw applied to the vacuum. Okay, so what's the final step? Great. So we are just, what remains is just to put w equals 0 and then just cancel z to the n factor. So now put w equals 0 and divide by that's it. So is it clear? Once again, the proof is rather simple, but this statement is rather strong. So this means that this locality property, although it looks rather innocent, is very, very kind of strong assumption. So, Anfisa, some questions? Well, just once again, let me repeat my request. So please ask as many questions as possible. So this makes life easier for me. Okay, so please repeat. So what's your question? So we know that this a of z, yes, from the this assumption, yes, so that a of z is local with all y of bz. Okay, so this means that there exists some n such that after multiplying by z minus w to the n, you can interchange the order. Okay, and this makes it.
Such that we can change order of a of z and y of u and also order of y of b.
Absolutely. Absolutely. So it should be maximum of two numbers. Okay. So this is the first kind of general claim which we need, and now now let us write one more formula which is going to be useful. So yes. So let us write. So if we have a Virasoro vertex parity algebra, then T of z some Lm z minus n minus 2. And then if we apply T of z to the vacuum, so it starts with L minus 2, L minus 2 vacuum plus z times L minus 3 to the vacuum. So, absolutely. Right. And so we see that this L minus 2 to the vacuum shows up as the free term on the right hand side. So the dimension of the field, or but where? So I mean, how to say? So you see this these fields, yes, they kind of they are defined by the structure of the vertex quadratic algebra. So for example, you see here this shift somehow means that we have degree n operator. So you see, since we have this degree 2, so we put here the n minus 2. How to say? So it depends on how you write the fields. So in our convention, so all the fields are written like y of az sum an z minus n minus 1. So in particular, if you would write it for t of z, you would have not ln but ln plus 1 minus 1. So this makes the difference. But you see, this is convenient because you can write this formula in a uniform way. But of course, you can keep track of the shifts, and this makes the difference. Okay, so then we claim that y of az vacuum is e to t a. Okay. So, sorry. Yes, yes, which comes from the definition of the vertex quadratic algebra. So, how to prove this? Yes, yes. So first of all, the important thing is that so we know that y of az applied to the vacuum equals to a plus a minus 2 z times a minus 2 vacuum plus z squared a minus 3 vacuum plus so on. Okay, and in particular, y of az vacuum at z equals 0 equals to e to zt a at z equals 0. Now, both sides, the left-hand side and right-hand side are series in Z, Taylor series in Z, and therefore, well, it's enough to check that. So it suffices to check that dz y of az applied to the vacuum equals to dz, well, it equals to a. That's it. Where? Yes, but you see, this already a is a vector, right? Mm-hmm. So is it true? Oh, let's understand why it's enough.
same differential equation. In some sense, if we differentiate.
But first of all, yeah, before we prove this, so can you explain why this is enough? So why, if we check this, then we're done.
We can subtract and then check it for that both sides are equal. It makes it zero.
No,
of difference is zero. Then difference is constant, right? X is equal or z equals.
Okay. So now why this is true, Timur? So what was your suggestion?
We can write it.
So yes, by definition, so the left-hand side equals to commutated t and y of az applied to 0. Okay. So which is equals to t y az 0. Okay. So how to proceed? So what about the right-hand side? So what is this? So I mean, maybe let me write it separately. So also dz p zta equals to t e zta. Yes, this is just from the definition of the exponent, right? Okay, so can we conclude now? Something? We can. Right? This is possible. So
if you consider dz minus t,
yes, yes. So both sides are solutions of the equation dz minus t something equals 0, right? So this means that we have two solutions of one first order differential equation. Both are serious, yes, and we have that the free term is the same. Okay, so we conclude. So therefore So maybe I put it in the wrong way. Maybe how to say this is not actually the way we are doing. So maybe let me write like that. Apply to is better, right? Okay. Good. Okay. But then, Andrei, did you manage to turn on the recording?
Yes, start.
Very good. Okay, so I hope that if I raise this grass, the hammer won't fall down. Let's check. So far, so good. Okay, but the sun is safe. Not really. Not really. So I mean, you see, this is not the equality of fields. This is equality of series with coefficients in the vector space. Okay, so so maybe one remark. So in the, you remember that in Quadrat's uniqueness theorem, we are saying that A of z applied to 0 equals to y of AZ applied to 0. And now we know that this is actually equal to E of zt applied to A. Okay, so this means that so it's enough to say that A of z0 at z equals 0 is A, and that you take the derivative of A of z applied to 0, then what you get is t is okay. So this is just a reformulation, but might be useful. Yeah. Yeah. So this is just a part of the word that's okay. So this is the remark, and now let's derive one more corollary. Saying that y of TAZ equals to dz y of AZ. Okay. So we know that, so this is not exactly a definition, yes, because so in the definition we know that if we take the commutator of t with y of AZ, then they should give us the derivative, right? So this was the definition. And now the claim is that actually if you want to consider the if you consider the image of our vector A with respect to operator T, then this is the derivative. Actually, I think this was one of the question maybe Andrea asked, if we can realize the derivative as a field corresponding to something. And this is actually the answer. So how do we prove it? Indeed. Yes, so by the Goddard's uniqueness theorem, it suffices to check that y of TA that dz y of az applied to the vacuum equals to y of gaz applied to the vacuum. Yes, because we know that this field is local with any other field. So since this is derivative, yes, you remember we checked this, that if some field is local with another field, then its derivative is local as well. So we only need to check this one. How do we do this? Right. So this is the same as saying that this is dz, and here I put e zta. Oops. And this should be equal to e to z t to ta. And this is definitely true. Okay. So because t commutes with this e to zt, so no problem. But once again, so the proof is the statement. So the proof is one line, but the statement is again not trivial. Yes, I mean from the definition of the vertex operator algebra, we only know what is the commutator of the field with t. And here we are saying that if we somehow apply t to any vector, then the result is very simple. So I mean the corresponding field is just a derivative of the field we started. Good. So, well, I mean, these all are kind of general statements about vertex operator algebras, rather important and useful, but so far not really kind of coming or related to OPE. And now let's do more technical, but also maybe also interesting statements. So the next is probably the symmetry, or do I need something else? Let's see. Yeah, maybe first we need the formula for the conjugation. So the conjugation lemma. So this is in the spirit of what we've discussed so far. So I take A from B and I write EWT, Y of A of Z, and then E to minus WT. So I conjugate Y of AZ with an exponent of the translation operator T. And then the claim is that it's Y of A is equal to So what do we actually need to say here? Do we need to say something so to make this formula somehow? No, I want to make it to state it in this full generality. Yes, so not only on the vacuum but everywhere. But I'm saying that if we write it in such a way, it's not really rigorous yet. So I mean, the two guys on the left and on the right are living in different spaces. Well, let's see. What is the left-hand side? So it's an element of what? No, in the left-hand side, so you're saying that the degrees of W, yeah? Yes. Yes, but this could be a problem for the proof. But I'm saying that so far we have a problem that the spaces, the objects are of different nature. Yes. Yes, by the very definition, this is the sum an z plus w to the power minus n minus 1. So this is the expression.
To understand this, maybe yes, series in the expand geometrical progression in different.
Yes, we have to. Yes, because otherwise, so this is a rational function. Yes, so we have to say what is 1 over z plus w. Yeah, that's right. So the choice is 1 plus w over z. Okay, so it's okay. And then we can work with right and left hand sides as series in z and w. Okay. Вот. Мгм. So you see, what is the problem? What do we know about e to wt y of az e to minus wt? So this is an element of what? So the this is a series in z and w, and the coefficients of the series are elements in and b, right? And now so we have z and w, and actually in w all the coefficients are, all the degrees are positive, yes, so we don't have actually negative coefficients here. And the in front of each power of w, the coefficient is an element in here, right? So this means that the right hand side should satisfy the same property, yes? So it means that, so if we write it in this way, so this guy sits in C of ZW. Okay, so if you if we fix, so this is a series. So I hope we'll show that it also has no negative degrees in W. But I mean, if we expand it in this way, yes, so then we have the series, which is given in this way, and then it belongs here. Well, I mean, it's like the expansion for delta function. And it's different. Okay. So, oh yeah, maybe we'll prove it and we'll see how it works. So, how should one work with this? So, any suggestions? Yes. But this is absolutely formally. Why not formally? So I mean, if you take the operator, which is the commutator with some operator, then its exponent is the conjugation with the exponent of this operator. Okay. Okay. So now, what is this? By the so it's the sum n equals 0, 1 over n factorial, and here we write add a joint operator of wt to the n and y of a. So say it again. What's this? Y z derivative. Yes, that's fair. Okay. And you see here we indeed have only positive degrees of W, and in this expansion we also have only positive, not negative degrees of W. So this match, and actually this is just a Taylor form. But once again, it's very important to know that Taylor formula, but these are not functions in the usual sense, yes? So these are series. So it is important to say how do we expand, and this is how we. Okay. So any questions so far? Uh-huh. Yes. Yes. So just like in the usual situation. So we have two series in say W, and then we just check the limit. By the way, any question to the audience in Zoom? Any questions? Any comments? Remarks? So are there still two people there, or two people? Okay. And now probably the last thing we need for the proof of the OPE is the so-called symmetry property. Saying that y of A of z applied to B is the same as y of B minus B A. Let me not to confuse. Just 1 second. Let me put it like this. Okay. So this is a kind of skew symmetry. So you want somehow to apply y of AZ to B, or you want to apply y of BZ to A, but they are not equal in any possible sense. But what you have to do is, first of all, change Z to minus Z. This is why the skew, maybe I should write skew symmetry. And also there is an operator e to zt, which has to be applied to make the equality. Okay. So let us prove the claim. So any suggestions? Hmm? Mm-hmm. So indeed, the idea, you are absolutely right. So the idea would be to go to the vacuum, yes, because so this B and A, they are kind of, they have to be somehow related to the vertex operator. So we can write that y of AZ B equals to y of AZ, y of BW to the vacuum at W equals 0, right? Then what else can we do? Yes.
Express A as y of AW.
So let's write, yes, so let's write like this. So just we want to make use of the formula we've just proved. Where this one. Yes, so namely, so we have this EZT here and YB minus Z. And what I want to do, I want to put the W here. And I want to write E to minus zt. And the remaining thing is e to zta and at double equals 0. This is the right hand side. And this is the right. Okay. So I just what I did on the right, I just added 2 times e minus zt and added this w here. So then this is equals to what? Yes.
We can use the formula from there.
Okay, so this is the right hand side. Absolutely, absolutely. Okay. And then the remaining thing, so what remains? How to show that this is indeed the same?
That if you have 2 local fields, then they get the same. Oh, I noticed it in the commutation.
Well, this is the statement. Yes, in principle. So, but then the only thing we can say that if we substitute w equals 0, so we're not claiming that they act in the same way on the vacuum. Yeah, so this is somehow stronger, and I'm not sure it's true. But what we can do is we can substitute. Well, you see, what we can do is we can substitute here w equals 0, right? So we are not saying that they're the same. Yeah. So no, I'm not just before substituting w equals 0. We can't say that this can be somehow extracted. So I mean, you see, if you have a series with 2 variables, S, Z, and W, and then the product of 2 guys is 0, then you can't say that one of them is 0. So this is true for the series in 1 variable, but not in 2 variables. So you see, we have delta function, which is a series. And then if you multiply it by Z minus W, you get 0, but the delta function is non-zero. Okay. So what we can do, we can substitute W equals 0, and then divide by Z to the n. So what is true, indeed, that this guy equals this guy, but only at W equals 0. Probably this is what you're asking, yeah? But not before substituting W equals 0. And divide by okay. So once again, the proof comes from what we've done already, but the statement is, well, not that simple. Okay, so now we can formulate the OPE and prove it. So this is again the main feature, the main object, the main theorem for today. So let me formulate it in the following way. So let us write three expressions. So yeah, let us fix. Let A, B, and C be three vectors and V, and then the expressions y of A of Z, y of B of W, C, y of B of W, y of A of Z, C, and y of A of Z minus W, B, W, C are the extensions of one element f of A, B, C in V of ZW and Z inverse W inverse Z minus W inverse. Let me check if I wrote everything correctly, and then we'll discuss. Yes, A of Z minus W, B, W. Yes, so I probably have to say, so maybe you can say me. So where does this element live? Where does this element live? So it's an element of what space? Say it again. So what are the coefficients? So the coefficients are vectors, okay? And then okay, or vice versa.
They can be negative, but they are not.
It's
So let's see. So what is written here? Here is written that this guy is a series in W such that the number of negative degrees of W is finite. And this is true here, yes, because as you said, you apply it to C, and the number of degrees of W is finite. But you can't say this for Z, right? And similarly, this guy lives in V of W of Z. And what about this guy? Where does it live? So maybe we better, so first of all, I this. And maybe since So we've never expanded this so far. Let me do this. So just to see what is this. So y of a of z minus w. It looks frightening from the first glance, but actually it's not too frightening. So this y of, what is this? This is the sum, n and z. Y of a n b w and z minus w to minus n minus 1. And I put w here. Okay. Oh, what did I do? I'm sorry. Too many y's. It's better now, I hope. Is it? So we have the outer y, and inside we have just, I expanded this guy by the definition. Okay. And you see, this is exactly what we expect. So this is the sum from z, y of a and b, w, g minus w to the n plus 1.
All the y's are linear, but so the names themselves will also
Well, this is a actually good question, but you see, the sum is indeed infinite, but since A is a field, it does not have too many negative powers. And so, of course, we'll discuss this, but the important thing is that here we say n from z, but in fact, the singular part is fine. Yes, so first of all, this should be understood as a constant. Yes, so this is z minus w to the n plus 1. So these are kind of constant. They are not constants, they are kind of rational functions, but they somehow do not contribute to the operator y. Yes, so they are.
I thought that w is both on the left side and the right.
On the where?
I mean, that means that one is w and w. I mean, inside y.
Yes. Why? Why don't you like it?
Because when we define y, or on the left hand side was just the vectors, some vector.
Yes.
And now we don't have series in w.
No, you are absolutely right. So I mean, this expression, this is just a short way to write something which might have no meaning.
So it's not correct.
So far, I mean, so far this has to be understood, and this is what we are going to understand here. So you see, there is no problem with this guy, right? So this is a nice and correctly defined element of this space. So this is also nice and correctly defined element of this space, but we have indeed to work a bit to understand that this is a well-defined element. And we'll just let's do this. This is what I'm trying to. So far, this is just a kind of, well, I can put quotes here. So what we're doing. So first we rewrite it by the definition, and this is going to be our definition. So actually, this is the object we want to work with. But let's try to understand that this object is well defined. And let's. It's a good point. Yes. we have to fix it. So in some sense, but before that, let's see that. So we will do it. But first of all, I'm claiming that this guy is an element in V of W of Z minus W. So do you agree with that? So just keeping Z minus W as a separate formal variable.
So we should consider this expression as the definition of what is.
Absolutely. Absolutely. So just want to say that this guy should be understood as an element in this space. So do you agree at least that this element in brackets is a well-defined element of the space of series with coefficients in V, and these are Lorentz series in Z minus W, coefficients in V of W. Just let's repeat that. So we don't have too many negative coefficients. So I mean, we don't have infinitely many, because A is a field, and therefore for n large enough, A and B is 0. So therefore, indeed, so in Z minus W, we have only finitely many negative Z minus W elements. And then if we fix the denominator, then the numerator is an element in V of, well, of course, I should put C here, yes. Because we know that Y of A and B is the field for any B. Okay. And now, in order to finalize, our claim, in order to finalize the statement, so we have to say, what does it mean that we expand such an element in here, in here, and in here? Well, this is also true, but just want to say that let's just explain what does it mean to expand it, for example, here. So what do we have to do? Inverse. Yeah, so here we have to define what is Z minus W inverse. Here we have to define also what is Z minus W inverse. And here, what do we have to do here? Okay. So for example, here indeed, we have to write Z inverse as Z minus W plus W inverse, right? And then expand as we are doing. Yeah, so to get here. Okay. So we don't want too many negative powers of Z minus W, so we write it this 1 over W 1 plus Z minus W over W. And then expand.
So in the first expression, we Z minus W inverse is what? It will be different things in the first and in the second expression.
Yes. That's right. Well, I mean, if you want to get here, so if you want to get here, then you don't want too many negative powers of W, right? So it means that you write it 1 over Z times 1 minus W over Z. And then you to get into here. So if you expand this, then you do have many negative powers, infinitely many negative powers of Z, but all positives of W, powers of W are positive. So let's see actually what's written here. Yes, so this actually explanation that actually this guy and this guy are indeed expansions of one and the same element. Yes, so there is an element in here. So they are the same, meaning that this element is the same for them. And actually we will see. So I mean, so far again it looks quite complicated, but let me repeat that the structure is very nice and we'll derive many consequences from this. But so first maybe one more remark. So remark. So the OPE is sometimes called associativity because operator product expansion. So sometimes this theorem and actually well, I have raised it, but the OPE is this formula. Yes, so it's sometimes called associativity because it can be written something like y of A applied to B equals to y of A times y of B. So this is very, very informally. Yes, you see we have here y of A of B. Here y of A times y of B. So in a sense, this is some associative operation. So you can somehow make it, get it out from the brackets. But once again, it's very informal. And however, so this is useful to understand that this right-hand side is indeed expression of this form. So it's like you take y of A with the actually variable z minus w, you apply to a vector B, and then you take again the operation y. So did I want to say something else? Maybe. Okay, so let us prove it. Maybe next time we'll discuss a bit more about the proof. So we want to prove the this theorem, and for that, let us let me put here. So we start with the expression y of AZ, y of PW applied to C. Okay, so and in a sense we want to get here and we want to get here, or want getting here from the very beginning, whatever. So let us first of all use this Q symmetry. So what do we know about this y thing? So this y of AZ. And now how do we rewrite this in terms of skew symmetry? So let me see if I have the same expression. Yes, I have the same expression. This is it. And let me now use, you see, I have this conjugation, this e to wt. So let me use the conjugation property, saying that this is e to wt, e to minus wt, y of az, and e to wt, y of c minus w. So why do I want this? Because so this is what? Right. So do I want something else? Probably not. Probably I don't want anything else from this. So we have e to wt, we have y of a z minus w, and we have y of c minus w. Okay. So this is it. Yes. And then let me try to do a similar thing with the formula y of a c minus w b w. So what is that? So I write this as the sum. B w over plus 1. Here I have c, and here I have c over n. Okay. So this is just the expression we have here, and this is just our definition. That's it. So what? Yes, and now I probably want to use the skew symmetry again. So I want to write the sum, and I put z minus w to the minus n minus 1 here, and then I have y of this applied to c, and this should be skew symmetric. So I put e to and what do I write else? I put y of minus cw, right? Absolutely. And I need a and b, absolutely, yes, yes. Okay. So is it similar to what we have? So now I probably want to combine this with that, right? So this somehow does not depend on n. And therefore I can write e to wt and y of c minus w. And the remaining part is y of az minus w. Okay. Say it again? Yes. This is the 2 star. Okay. Absolutely. Absolutely. Yeah. So by locality, star and 2 star are expansions of one element f of ABC. So this looks like a trick, but we've used several things. So the most important thing we are using is the skew symmetry, yes, which is based on the Goddard's uniqueness theorem and on the conjugation lemma, and also the kind of last point, the main thing. Well, the important point is that the star and 2 stars, they are just in opposite orders. The products in opposite orders of 2. Yep.
But if we use m about fields and expansions, we should say about matrix elements. Or we don't remember.
No, you see, so well, there are several formulations of the locality property. Yes, some of them is in terms of matrix coefficients, but one of them is that the 2 things are local if the expansion of the same element. So in principle, if we take matrix coefficients, this would mean that we also take the value of some covector on this guy, but this should be true for any covector. So just putting them all together, this makes sense. So any further questions? So once again, let me repeat that the logic of the whole story is that we want somehow to write the product of 2 fields as the sum of infinitely many fields, which are somehow generated by considering this product. But in order to make this precise, we have to work a bit. And this is what is happening here. So far, just consider 3 expressions, saying that these 3 expressions are expansions of the same element in some large ring. So we'll get back here next time and discuss this in more. So any further questions? Yeah.
How Vertex algebra is defined by singular
Well, I would say that the negative part, the singular part, is very important and it captures lots of information. But you also need, you see, how to say, so the singular part how determines you the n greater or equal than -1 or 0 greater than 0 thing. But you also need other terms to.
What part is defined by singular part? Somehow
commutator. Yeah, let's wait until the next week and we'll work it out in detail. So indeed, the singular part is very, very, very important. So in sometimes people are saying that vertex separated algebra is just a singular part of the OPE, but it's not the whole structure. You mean on the same vector space? Or no, if you fix the OPE, then the vertex separated algebra structure is defined because you see these guys are the same singular part. Probably not. Probably not. No, I don't think so. But still, the whole OPE is somehow a nice way to write it.
There is no way to recover.
Well, so you're asking if we know the negative, the positive operations, can we recover the negative? Yeah, by the way, we've seen today the Goddard's uniqueness theorem. So after all, it's just enough to know how the guys act on the vacuum vector. Yes, and this is only half of the series. Yeah, so should be fine. But I don't know if there is a explicit formula how you can write it. But in principle, just enough to, we've seen that it's enough to somehow act on the vector. Well, of course, if you change the yes, if you change the how you write it here, then you need to change here as well. I think only the degrees is changed. Well, maybe you have to say what is the singular part also in a bit more careful way. But so I mean, if you put the shift here and you put the shift here and you also put the shift here, I think then it's okay. So, but important is to do it everywhere. So of course, if you put the shift here, but you don't put it here, then something wrong will happen here. But if you put everywhere, it's further questions? Okay, if not, let's stop now. And I'll upload the homework on the webpage.